Greetings of the day to all who are present and who will be watching on the YouTube. So, I welcome you all to another doubt clearing session for the course Fundamentals of Electrical Engineering, being taken by Professor Debapriya. So, let's begin. Let me share my screen. What's the problem? Yeah. Let me notice.
Recording in progress.
Hmm. Okay, so last week we were discussing first order circuits. From today, we'll continue from that. So we stopped at resonance. So we discussed series resonance and solved a few questions on that. And then today we'll continue from that. We'll discuss parallel resonance and quality factor, and we'll start with one more topic, maximum power transfer theorems, and then we'll start with three-phase circuits. This is week 9. Okay, let's. So first of all, I would like to clarify one thing. So this question in my last class, none of you pointed out, but so the way I calculated, I assumed a few things, but the answer was correct. But you have to know how things would come into play. But I regressed a bit. But since so I want to continue with this question first. So first of all, what we are given over here is that so the reading of ammeter A1 is given, which is 8 ampere, and the reading of ammeter 3 is given as 18 ampere, and we were required to find out the reading of ammeter 2. Okay. So what's happening here is these both currents are vector quantities, right? So whatever we'll do first of all, whatever these ammeters are measuring are the RMS quantities. And what we are supposed to do is we are supposed to do vector addition on these A1 and A2 to find out A3. So what is A3 going to be? It's going to be vector addition of A1 and A2. And what exactly, how do we get this quantity through vector addition? We simply calculate the magnitude of A3 as follows: A1 square, A2 square, plus 2 A1, A2 cos phi, where phi is the phase angle difference between the two currents A1 and A2, right? So as you can see, let's assume that whatever current A3 was feeding into those two in that branch, let it be some I angle theta. Just don't go into the details, right? Now, so if we say, let's say that this R won't produce any phase difference, right? So what is it going to be? Let's say A1 is going to be some I dash angle theta, right? It's not going to produce any phase difference. But A2 is connected across a capacitor, and we know that capacitor, when so it produces the phase difference, and it makes the current lead by 90 degrees. So what's going to be? I double dash is going to be theta plus 90 degree. So what is phi in this case? The angle between A1 and A2. So it's going to be 90 degrees, right? So if you put it in this equation, you'll get the same value that I started with. Since cos 90 is 0, this term would be 0. So this is how it came out to be. And then we squared both sides. It came out to be A1 square plus A2 square. And then from that, you could easily find out the value of A2, which came out to be 16.12 ampere. So this I wanted to clarify before moving further. So let's start today's class. So let's start with parallel resonance. So last class we discussed series resonance. Now we'll discuss parallel resonance. Again, let's draw a parallel circuit. Let's with a resistance in parallel with an okay. So Renessa, your voice is breaking. Can you say it again? Hello. I am unable to hear you. Can you write it out in the chat box? Okay, so we'll continue. So all the three components, resistance, inductor, and capacitor, are are parallel to each other, right? Let this be a value of R. This would be J time XL, and this would be minus JXC, right? So let's find out. So in parallel, since so we'll try to find out the admittance. What is admittance? Admittance is the reciprocal of impedance, right? So the admittance is going to be 1 over R plus 1 over J times XL plus 1 over minus J times XC, right? Now 1 over R is conductance and 1 over X is called as susceptance. Right, so this would come out to be G plus, so this would be minus JBL plus JBC, right, where BC and BL reflect the susceptance of the inductor and capacitor, um, um, respectively. So this comes out to be J times BC minus BL, right? Now, as I've told you, so how do we find at what frequency a circuit resonates? Is simply by equating the imaginary part, equate it to zero, so that the complex term of the admittance or the impedance is nothing but a real term only, right? So if we equate this to zero, susceptance of capacitance will be equal to inductance. Let's write it. This would be omega naught C omega naught L, which comes out to be 1 over root LC, right? So, there is no difference between the resonating frequency of a series resonating circuit or a parallel resonating circuit, right? So this is our main what you can say finding from this. Now let's plot admittance versus frequency graph. So this is admittance and this is frequency. So we know. So this is yeah. So BC is what? As you can see, it's nothing but omega C, right? It's linearly increasing with respect to capacitance, right? Sorry, it's linearly increasing with respect to frequency. So this would be graph, and we know that since BL is inversely dependent upon frequency omega, so that means I don't have space. Yeah. So that means it would look something like this, right? So this is BL. And G is a constant term, right? So it would be this. So that means if we superimpose all of these three curves, what's our final curve going to look like? It will be something like since this is a very high value, it will start like this, come out to this point, and then start to increase, and then linearly increase. Something like this, not drawn to scale, so don't. So now at the point at which it intersects the conductance curve is nothing but our resonating frequency, right? Because that means the vector addition of BL and BC is 0. So that means here these two places. So which region will be inductive? This region will be inductive region, and this will be capacitive. So that's how our admittance versus omega curve would look like. What more did I want to discuss? Resonance, suspense. So else. Okay. Now let's come to a new term, quality factor. What exactly is a quality factor for a circuit? So a quality factor is generally it's used for energy storing devices when they are connected into a circuit, so like inductor or a capacitor. So for those we usually calculate quality factor, which is nothing but Q, which is equals to 2 pi maximum stored energy, right, upon the energy that it dissipates per cycle, right? So that's how we donate our quality factor. So it's done. Yeah. So let's start with an RL circuit. So can anyone tell me what is the maximum energy that can be stored in the inductor? Emax. So E is for E of an inductor is nothing but half Li square, right? So when the inductor current will be maximum, the energy will be maximum, right? Now, energy dissipated per cycle. What can be the amount of energy that can be dissipated per cycle? So, for example, a resistor is connected, right? It will dissipate what? I max square into R, right? So, energy dissipated would be I max root 2 because we calculate RMS square into R. Per cycle, we simply multiply it with frequency or divided by T, which is whichever is convenient, right? So if we do it, so Q would come out to be 1 over T, right? R Q max square 1 over T. Yeah. Um, per cycle, right? So it would be T per cycle would be upon frequency. So Q is what? 2 pi into half L into I max square divided by I max square by 2 into R divided by frequency. So these two terms will cancel out. What we are left with 2 pi FL upon R. What is 2 pi F? It's nothing but omega naught. So quality factor is omega naught L by R. So therefore, Q is omega naught L by R for a series RL circuit. Similarly, for series RC circuit, let's calculate. So we have a resistance in series with a capacitance. So energy dissipated per cycle is, no, sorry, energy stored per cycle. Stored, maximum energy stored, sorry, it's half CV max square, right? And energy dissipated per cycle, I max by root 2 square times R, right? Now, if I want to write this term in terms of I max, so what is it going to be? So it can be V max can be I max upon omega C, right? Simply it's the reactance multiplied by the I max term, right? So therefore, if we do this whole thing again, so I'm writing omega naught. Don't confuse it with the with what you say resonant frequency. It can be normal frequency as well. Should write omega naught L by R, right? So this means that we can write Q as 2 pi into half into C into and I max square by 2 into R by F. So this would get cancelled. So what we are left with is 2 pi F upon omega CR square CR. So 2 pi F is omega. So this would get cancelled with this. So this is 1 upon omega CR. Hence, for a series RC circuit, it's something like this. Okay, so we got both of these for these RL and RC circuit. Let's see for RLC circuit. Now, Since the maximum amount of energy stored in a capacitor is dependent on the maximum amount of voltage it will flow, right? So when capacitor will store maximum energy, inductor current will be zero, right? Because when so there is no other circuit, energy storing circuit present. There's a single R present, but it dissipates energy. So the maximum amount of stored energy in a capacitor will only be when the inductor current will be zero. And the same goes for the for the inductor. So when the inductor stores the maximum amount of energy, it's when I is maximum, which is at the um, starting of the circuit. So at that time, voltage of a capacitor is zero. So that means, and vice versa. So if you think that means that both of them will store the same amount of energy, right? Because there's no other energy storing element present. There's a resistor, but it dissipates energy, which is equal for both of those, which is independent of inductor and capacitor. So that means half CV max square will be equals to half Li max square. So that means for a series RLC circuit, Q can be both omega naught L by R or 1 upon omega C R. So that's how you write quality factor for all those three circuits, RLRC and RLC circuit. Right. So now I want to discuss one more thing. So as I told, so what would happen when at resonant frequency for a series RLC circuit, let's say at resonating frequency, I is maximum, right? So if we represent it through a graph, so this is I, this is omega, and let's say this is I max. So at omega naught, I is maximum, right? So okay. Now what happens? So at both of the sides of the omega naught, what happens is I starts decreasing because the effect of capacitance and inductance starts increasing, right? So what happens? Usually, so in this side, capacitance is more, and in this side, inductance is more, right? So if we draw roughly, this is how the variation of flat top, variation of current with respect to frequency would look like. So I'm not drawn to scale, but that's how it will look like, right? At half the power, what would happen? So let's say at P max, I'm saying the current is maximum. So let it be a let I max be a RMS current only. So it would be I max square R, right? So that's the maximum amount of current will flow because at resonant frequency there is no other impedance, right? So it's just R. Now I'm saying what would be the value at P max by 2? When so at what so I want to calculate uh, what would be the current when Pmax when the maximum power is half? Can you tell me what would be the value of current when Pmax will be half, Renessa? So if we can write it like this, right? Into R by 2. We can take 2 inside, which would be Imax by root 2 whole square into R. So this means that yeah. So at 1 by root 2 times Imax, which is 1 by root 2 is nothing but 0.707, right? Yeah. So 70.7% of the maximum current, the current at which the value of it is 70.7% of the maximum current, the power would be exactly half of the maximum one. So this is where 0.707 will lie. So these two frequencies are called half power frequency because at these frequencies the current the power is exactly half of the maximum power. So this the total what you can say the total range of frequencies at which the power is between half, exactly half, is what we maximum half times the maximum power is what we call as our bandwidth. So our bandwidth is nothing but the total range of frequencies at which the power is at least half the maximum power. So that's our bandwidth. So so let's talk about how we can get. So let's talk about some interesting factors or interesting equations with respect to bandwidth and quality factor. So since you're back, Renessa, you were trying to say something. Can you say it once more, or you can write it in the chat box too?
Sir, kindly discuss the generation of alternating EMF. There was a topic which was discussed in the video lecture, so you kindly discuss it once.
So single phase, right, or three phase? So I'll be moving to three phase after this, but if you want to discuss for single phase, we can do that. So I did it last time as well. So didn't you go through my last week's video?
Sorry, but I didn't. Well, I'll be seeing that video. Thank you.
Okay, if you see that, because I have to move ahead too, but I have discussed it with the help of a diagram over there, so you'll be able to appreciate how alternating EMF would come into picture. But yeah, we are also going to move ahead to three-phase circuit. There also I will discuss briefly, but you will be better able to appreciate this concept when we discuss alternators or synchronous machines, which we are going to do in the upcoming weeks, right? So yeah, that's it. So what was I? Yeah, I want to discuss some specs related to half power frequency. So right now I'm calling it, but I'll for brevity reasons, I'll call it omega 1 and omega 2. When I say that, just remember that it's nothing but half power frequencies. Okay. So I've told you, so below omega naught, our a series RLC circuit behaves capacitive, right? And above omega naught, um, it behaves inductive. So there's one more concept that I wanted to discuss. Okay. Mm, okay, let's discuss first. Hmm. So let's discuss what happens at half power frequency. So at half power frequency, I told that the circuit so if it's less than omega naught, so if so omega one is less than omega naught, which means circuit behaves capacitive. And for omega 2, which is greater than omega naught, its behavior is inductive. Now, what happens is usually at half power frequencies, um, so R by root 2 R by 2 as well. Just a second, let me see. Hmm. Yeah. So what? Yeah. So at half power frequencies, I told you I1 is nothing but the maximum. Let's call it I naught. Yeah, let it be I max by root 2, right? And I2 is also I max by root 2. Now we know I max comes from the fact that C is equals to V max by R, which means sorry, yeah, which means I1 is equals to V max upon R root 2, which is equals to I2. So now I'm saying that our what you say inductor is the magnitude of the impedance comes out to be R root 2, but we know that for our circuit we have a capacitor and an inductor in series with the resistance, right? So that means since the magnitude of Z is nothing but R root 2, what does that tell us? Can you tell me? So since magnitude is nothing but R square plus XL minus XC square, and I'm saying it's equal to R root 2. What does that tell us? It tells us that R is equals to XL minus XC. You square both sides and then tell me if this comes out to be true, right? So at half power frequencies are the difference between the reactances of inductor and capacitor. I should write it like this mod because both are it can be capacitive or inductive in nature. So yeah, so XL minus so what was I saying? Yeah. So resistance is equal to the difference between the reactances of inductor and capacitor. So it's a very interesting thing. So that means theta is what? Can you tell me? Theta is 45 degrees, right? So since so that means I1 is what? I not oh sorry, I max upon root 2. Should write it like this magnitude. Yeah. So the pictorially it would be represented as since it's a capacitive circuit at less than omega naught, 45 degrees, capacitive as omega 1 is less than omega naught. And I2 is what? Right. So this is what our circuit equations would look like. Now, I told that at omega 1, mod of XL minus XC is equal to R. So Renessa, can you tell me if I open this modulus, what would come? Would it be a positive quantity or a negative quantity? So since omega 1 is less than omega naught, xc would be greater than xl, right? So it would open as a negative term. So that means xc minus xl is equal to r, which would tell me that, okay, 1 minus omega 1c. So similarly, if I write for omega 2, what will be the value? Can anyone tell me? It would be omega 2 L minus 1 upon omega 2 C, which would be equal to R. So we got two equations. Now let's subtract 1 and 2. So what will we have? We will have 1 upon omega 1 C plus 1 upon omega 2 C is equals to minus omega 1 plus omega 2 L, which is equal to 0. So if we rewrite this, this could be written as omega 1 plus omega 2 upon, right? So we can cancel this out, which means omega 1 omega 2 is equals to 1 over LC. What is 1 over LC? Omega naught square, right? So that means omega naught is the product of the half power frequencies. So you have to remember this. If let's say a question comes and they have given you just half power frequencies and you need to find out the resonant frequency. So how will you find out? It would be found out only by using this relation, right? What's more? I discussed the concept of, and I discussed how half power frequency. Just that's it, right? Hmm. So these are, one more thing. Um, so I'll tell you to do it yourself. So there's one more relation that comes out to be that a quality factor is given by omega naught upon bandwidth, which is nothing but omega naught upon omega 2 minus omega 1. So to find this out, what should you do? Add 1 and 2 and check, right? I'll give you this little exercise to do it yourself so that you also know how this relation would come into play. So let's move on to further topics. So one more topic I want to discuss is maximum power transfer theorem. Yeah. So so as I told you earlier also, so we discussed this in Thevenin's theorem, right? So we said for maximum power, what we did, we checked if there is a variable resistor, and we calculated power with respect in relation to that resistor, and then we did the differentiation with respect to that resistor only, right? So we are going to do the same thing over here, but as you know, there will be two separate cases. One where there is just a variable resistor in series with a source impedance, and there is one more that could be variable impedance, right? So let's do case one, variable resistive load. So we have this, like, is Z, G plus JXG in series with the variable resistor. So how are we going to do this? Can you tell me? So can you tell me the equation of P with respect to load resistor, Vanessa? So how will you do it? Just find out the value of I and then tell me. So I know it's P is I square times RL, but I want you to tell me the full equation. So I is what? Vg upon Rg plus RL plus J time Xg, right? So magnitude of which comes out to be, right? This is correct. So equate, so Vg square RL, Rg square, sorry, Rg plus RL square, Xg square. So again, so in the similar way, differentiate with respect to RL and equate it to 0. So can you tell me what would be the differentiation of this load power with respect to RL? Let me know if you're doing something. Yeah. So simple. So the denominator is squared. So Vg square, keep the denominator constant. Right. And the below would be, right? Hmm. And this would be negative.
So then it will be RTS plus RL whole square plus XL plus अच्छा wait x g whole square plus v g square plus RL 2 r 2 into whole 2 into RL plus RG is equal to 0. Then RG square plus XG square plus XL whole square is equal to.
Hmm. So if you rewrite this, so can you tell me the final answer? So tell me what is the final answer of RL? I'll wait. 2 Vg square RL. Hmm. Oh, this is right. Hmm. Okay, so I'll do it. This is Rg square RL square plus RL Rg.
It will be RL minus RG is equal to 0, so RG is equal to R.
Okay, so for me it comes out to be RL square equals to Rg square plus Xg square. Is that what you were talking about? So RL comes out to be under root of Rg square plus Xg square, which is nothing but the magnitude of Zg, right? So if this is your answer, very good, Nanessa. So that means when RL is equals to the magnitude of Zg, power will be maximum. So this is one case. Now let's do one more case where we have a variable impedance. So again, we have some Oh, sorry, this is not DC only. Right. So now, what will be the value of I? I would be Vg upon Rg plus RL plus J times Xg plus XL. Now, can you tell me when I will be maximum? So for let's talk about XL first. So in the denominator, if XL is equals to XG, the imaginary term will vanish, right? So that means if XL is equals to negative times XG, it's just a real value RG plus RL, right? Now, at what value of RL do you think? So I shouldn't like take this. This is good way of writing. Let's write in terms of magnitude because that's what we are concerned about. So this would be, so if XL is negative of XG, the impedance would be only resistive in nature, right? So that means I is what? Vg upon Rg plus RL, right? Now tell me, what would be the at what value of RL will the circuit have, let's say, maximum power?
So on further solving, it will be I is equal to
Mhm.
Vg by Zg plus Zl. Then if we substitute the impedances, it will be I is equal to Vg by
It's
Rg plus G
so
uh,
you don't need to
plus.
solve it in full, Renessa. So from previous lectures, you'll know when we solve for Thevenin, it's just so now it's all real values, right? So for Thevenin, at what value would did that come out to be maximum? When it was equal to that source inductance, source resistance, right? So similarly, or sorry, Thevenin resistance, right, which is source resistance only. So similarly here also, it would be maximum. I would be maximum when RL is RG, right? You can solve it full. The same thing you'll get. So you can go ahead and do that. But if you don't do that, this is an easy way to know because you already know from previous analysis that when the load resistance is equal to that of source resistance, our power is maximum. So therefore, our ZL will look like RG minus JXG, which is nothing but the conjugate of ZG. So, so any trouble, Renessa? I hope not. So if you solve it to do Vg square upon Rg plus RL
So
whole
it is
square
the
in.
conclusion that the maximum power will flow through the AC circuit when the impedance on the load is the uh, conjugate. It's a complex conjugate of the source impedance.
Yeah, yeah, that's what we got, right? We took XL as negative of Xg and RL it would be Rg only if we solve this, and we'll get this only, right? The conjugate of the source impedance. That's what I wrote. Maximum when load impedance is conjugate of source impedance. Any doubt? So let's solve a few questions based on this, and then we'll move to three-phase circuits. What I want to discuss. This is a three-phase. Yeah, this is for single. So what we are given in this question, so you can see it clearly, right? You can solve it with me. It's given that we have a single phase 50 hertz 230 volt RMS source, which is supplying three loads in parallel. 2.4 kilowatt ampere at a leading power factor of 0.8, 4.88 kilowatt at lagging power factor of 0.9, and then a 900 watt at unity power factor. A capacitor is connected in parallel across the parallel combination of three loads so that the current supplied by the source is in phase with the source voltage. Find the value of capacitor. So that means if the current supplied by the source is in phase with that source, the source voltage, that means the circuit is resonating, right? So what we are given here is we have a source voltage 230 volt 50 hertz, which is supplying three loads Z1, Z2, Z3, and a capacitor. And and it's telling us to find the value of capacitor for which this whole thing would be maximum. So any idea how we can do this? So first we'll calculate Z1, right? So what we are given, it's taking 2.4 kilovolt ampere. So that means 2.4, or we'll write 2400 volt amperes of power at PF equals to 0.8, which means theta is what? Cos inverse of 0.8, right? So it's 38.87 degrees. So can you tell me the relation between, so this is S, right? Apparent power. So can you tell me what is the relation between Z and apparent power? Nessa. So the magnitude
No,
of
I
Z1.
know it. The complex power, the derived by source equal to the apparent power.
Mm-hmm.
Just give me 1 minute, please.
Yeah, yeah. So Z is V upon I, right? Multiply V both numerator and denominator, you'll get V square upon VI, which is nothing but V square by S. So that means 230 squared divided by 2400. So let's find out its value. It came to be 22.042.
You
Now,
showed it to a power triangle, the previous.
mhm. Yeah, yeah. So you can do through that as well, but it's more convenient to write it like this so that you can derive the formulas on the go. So now I have our what you can say the magnitude of impedance. Can you tell me in polar form what should I write as an angle? Would it be positive 38.87 or negative 38.7, given that our the current it draws is leading? Can you tell me?
have positive.
So, okay. So what was I saying is, since Z1 is drawing a leading current, right? Leading current with a leading power factor, and the angle is given by 38.87 in polar form. Should it be plus 38.87 or negative 38.87? It should be negative 38.87, right? Capacitor. So, in similarly, can you tell me what would be the value of Z2? So we are given that it's
Okay, now I
drawing.
remember. You said that true power P is equal to I square R and reactive power is equal to I square X and apparent power is equal to I square Z.
Uh, um, y- yes, you can say that if you, but yeah, you can say that. So can we go ahead and do this question? So what was I saying is Z2 is 4.88 kilowatt at lagging power factor of 0.9. So so tell me quickly the value of Z2. 0.88 kilowatt, 0.9. Yeah. So theta is what? Cos inverse 0.9. So can you tell me if you found out? Okay, so Z2 is what? And we know P 4.88 into 10 raised to power 3 is nothing but VI cos theta. So multiplying mod of V cos theta both sides will get V square cos theta upon P. So that means 230 square into zero point 0.9 divided by 4880. 9.76, right? That's what you got. Now, since
Sir,
it's
my
drawing
answer is 8.3.
8.3, no, it won't be 8.3. So it's V square cos theta upon P, right? Just a second, let me see. P is 4880. So it's power. It's not apparent power anymore. It's real power, right? So did you do it using real power value only?
Yes, sir, I did.
Um, just a second. 250 square into zero point 0.9 divided by 4880. No, in essay, it comes out to be 9.756 only. So can you tell me how you did that so that I can help you with it? Yeah, Nissa. Okay. So
No, I
we'll
didn't get the answer still. Just
okay. So see, Z is what? V by I, right? So we're calculating magnitude only. So we know what the phase angle difference is. We need the magnitude. So by magnitude, we know it's mod of V upon mod of I, right? So so I know the value of VI cos theta. So I multiplied V cos theta both numerator and denominator. So we got this term. Just a second. We got this term. And then from that, I know mod of V is 230 square into zero point 0.9 divided by 480. And if you solve this, the answer comes out to be 9.756 only. So I don't know where you got it wrong. So that's how you're supposed to solve it. So we'll move. You let me know if you're still having a difficulty finding out the answer. Can you solve it using this also? V square cos theta upon P. Cos theta is
Okay,
zero
I'm
point
sorry.
0.9, right? Cos theta is 0.9. So don't take it 0.8 if you're taking it to be 0.8.
Yes, sir, now I got 9.756147.
Yeah. Great. So third, we are given as 900 watt of power at unity power factor. That means it's what? It's a resistor, right? It's flowing at unity power factor. So it would be nothing but V square upon P. Can you tell me the answer quickly? P is 900, so 230 square upon 900. So it comes out to be
The answer will be
58.7.
68.7.
Yeah, great. So we got all those three values, and now it's saying that it's connected across. Okay. So we got Z1, Z2, and R. Can you tell me what it would be the equivalent admittance? It would be 1 upon Z1 plus 1 upon Z2 plus 1 upon R. Can you quickly find out the value of admittance for me? Let me do it with you. So you have a calculator, right? You got a calculator or not? So the answer I'm getting is 0.1446 minus 0.016 to iota or j, whatever you say. Great. So we got the equivalent admittance as this. Now it's saying that we are connecting a capacitor. So let's call the susceptance of that capacitor be J upon XC, right? So Y plus JXC is what? 0.14. Sorry. So 0.1146 minus 0.0162 J plus J. So the susceptance of that capacitor is equal to the value of 0.0162, which means omega C is 0.0162. C is 0.0162 divided by omega. What is the value of omega? 2 pi f, right? F is 50. So it will come out to be 100 pi. So if you find it, what would be the answer? So I'm getting 5.156 into 10 raised to power minus 5 farads, which we can write as 51.56 microfarad. So at this value of capacitor, our circuit will resonate and the phase difference between the supplied voltage and
So
current will
I
be
got
zero.
the answer as 0.51592.
0.0159. 0.0162 divided by 100 pi is,
0.5159.
can you tell me in microfarads? Just tell me in microfarads.
51. I'm rounding it up and it will be 51.6.
51.6, right? So 55. I guess there's, so the answer should be none of the above. because it's 51.56. They have given us 55.56. Is there a mistake? Um, okay. I guess there's a mistake in the question. So three digits are matching. So it's B only, but it's 51. So you can do one thing, none
But
of the
in
above.
the previous class, the question you did, and it had a very similar approach to one of the questions which was asked in the assignment. So I
Hmm.
got it wrong, sir.
Okay, so the similar question was asked this on similar pattern. Can you tell me which question? Which question? Which question? So can okay, just a second. Your voice is breaking too much. So can you tell me which assignment or which question in the chat box, and then I'll tell you. Did you write? Assignment 8. Okay, let me open. Okay, let me share my screen. Okay, let me see. Let me see. Just give me a moment. Yeah, just a second. I'm opening. So is my screen? I'll share. Okay, so you can see my screen, right? So let me open the course. This question, week 8, assignment 8. If A1, A2, A3 reads okay. Under events. Answer is 16, right? The answer is correct. Where did you find it wrong? So it would be under root of A3 square minus A1 square, right? Vanessa? Okay, I'll take a screenshot of this question so that we'll discuss it using.
No, this I
Mm-hmm.
meant that this answer is correct, but when I did using your method from the previous class, I got it wrong, and also the solution also I got it wrong.
No. So even though the way I told you to calculate it was, so I didn't tell you the whole story how it was just A1 square plus A2 square whole root, but the answer should have been correct. So let me tell you. So let me share the screen first. So I didn't tell the whole picture how. So my screen is visible, right?
Sir, I got the answer is 19 point something, which was rounded up to 20.
Mm, so just give me a moment. So I took a screenshot of that question. So it was the same RC circuit, right? It was just the values were different. Am I correct? So can you tell me? So earlier also I used this equation only, but I didn't tell you how this equation came from. How cos phi was zero because it was an RC circuit in sorry and a capacitor in parallel to R, and it would produce a phase shift of 90 degrees. But you will use the same method, right? So let's do it. So A3 reads 20 square, A1 is 12 square, A2 square, right? So A2 would be what? 20 square minus 12 square. So if you do it, it's 16 ampere only. So I don't know how you got it wrong. So last class also I told this only, that it would be A3 is nothing but square root of A1 square plus A2 square. So either you calculated it wrong, or because, let me open my notes from previous day. Here. So it was A1 square minus, sorry, A3 square minus A1 square. So that's what we did. So I don't know how you got it wrong, but the method was correct. It's just that I
So
didn't tell
there
you how.
is another question which was from this book of hat, and there also the answer, like there was one of the assignment, uh, and the question, mostly the questions are from this book called hat, and that answer
Book
also
called? Book
I
called? Book
found,
called? Book called?
and that answer was also found wrong. I mean, not wrong, but the book solution was a bit
Okay, you do one thing. You write that. You write me to this email ID I've already provided, and I'll send your query to the instructor. That's the most I can do, because I'm a TA for just the doubt clearing session. I don't have a control over the questions, or what you say, the checking too. So that's being done by IIT Kharagpur only, and I'm here at IIT Kanpur. So I can do one thing. I can forward your query to the instructor. That's all I can do. So I've shared my email ID. You can write to me, and I'll share it to that instructor. Anything else? Is it all? Okay, let's move ahead. So because if any question is incorrect, it's incorrect for everyone, right? So if it's better if you bring it to the notice of instructor, and he'll be the one who can change it, or who will send you an email. So let's do this question. So what's it saying? It's saying that a voltage VT is across the terminal A and B, which is a sinusoidal voltage with angular frequency 314 radians per second. That means it's 100 pi. We have to find the value of inductance L in such a way that the inductor current is in phase with voltage. So that means what we just do, what we did previously, equate the imaginary part to the zero, so that the complex term is just the real part. Let's do it. Let's first calculate the admittance for this thing. So what is the admittance for this? It would be 1 upon 100 plus J PC, right? So 1 upon 100 plus J omega C, which is 314 times 10 raised to power minus 6. So can you quickly tell me what is the value of admittance for this? Sorry, value of impedance, which is nothing but 1 over admittance.
So in the engineering circuit analysis in the 8th edition, the answer was matching. But when, like in the 11th edition, it wasn't.
Okay, so where are the questions taken from? I didn't get the book name. So can you tell me what is the book name?
From engineering circuit analysis.
By whom? Author. I'm asking about the author. Vanessa, if the questions you feel that the answers to some questions are wrong, I can discuss over here as well. So you can let me know which question you feel, and then let's solve it. Let's see if it's incorrect or not.
Question is not wrong, but the answer is 7 days,
Yeah, yeah,
and
yeah. Yeah.
in the edit.
If the answer is wrong, you can let me know. I gave you my email ID, right? I'll forward your query to the instructor because he has the power to change your what you say to change if any answer is wrong or incorrect in the assignment. But I'll tell you to wait first. Let them upload the solution sheet and then go through it and then write to me or instructor because in that way you will be able to. So if there's something wrong, they can also know, right? They'll also solve it. So they'll change the answers then only. So wait for them to upload the solution sheet. Or if you are curious, you want me to do something, just write to me and I'll forward it to that to the concerned instructor. That's most I can do. So can we go back to this question? So I was asking you to calculate the impedance, which is one reciprocal of admittance. Can you tell me? It's 99.9, 3.137. Right now, Renessa, can you tell me if this is in series with this inductor which has JXL impedance, right? Or reactance. So that means XL should be equal to 3.137, right? So XL should be equal to 3.137 or the imaginary part of Z. So that's what we were supposed to do. So so that means omega L is 3.137. We should call it omega naught L. That would be, and L will be what? 3.137 divided by 314, which tells us it's nothing but so 9.99 millihenry. So none of the answers match, right? So answer is none of the above. So as you can see, solving questions based on resonance is very easy. You just try and calculate the try and equate the imaginary part to zero, and then you'll get the answer. If you're required to calculate the value of inductor, capacitor, or even the frequency at which it resonates, it's just equating it to zero. Let's go on to next question. So it's saying for the value of L obtained in Q3, find the quality factor of the circuit given in figure 3. Okay. So quality factor is what? Omega naught L by R, right? So we know omega naught it's 314 only. L we found out it's 9.99 into 10 raised to power minus 3. Now what is R? Is this 100 ohm resistance R? I mean, um, so 99.9 is also 100, but yeah. So whatever the equivalent impedance you found out, the real part of it is the resistance, right? So you calculated the equal impedance of this parallel structure, and you equate it to this its equivalent series structure, right? So in its equivalent series structure, what is the value of whatever is the value of R, you go ahead with it. So right now it's 99.9, but had the capacitor value been different from 1 microfarad, it should be 2 or 3, it would have been a different value. So if you write, it would be something like 99. So what is Q? So it came out to be 0.0314. So that means this answer is correct. See so this is, so it's very easy to find out, to solve these kind of circuits. You just have to know all of the equations, the relations, and then it's a piece of cake for you to solve these questions. Let's go ahead with another question. Okay. So what have we got now? So it's saying that for the circuit shown in figure 5, it is observed that for supply frequency 60 Hz, the magnitudes of VL and VC are 2 times of VR. Find the inductance. So that means VL is equal to what? 2VR, and VC is also 2VR. So if we do KVL, so V is equals to VR is 4VR. So mod of VR is what? 5 upon 5, right? So it's 1 angle 0 only. Just don't call it mod, call it VR only. So that's how it would look. No, not like this. So they have given magnitude, right? Sorry for that. Yeah. So they have given. So they have given magnitudes, right? So that means mod of V is equals to mod of VR plus 4 times mod of VR. That means VR is 1. So now if mod of VR is 1, the magnitude of voltage of resistance is 1. So the current, which is also equals to the current of the whole circuit, is nothing but 1 upon 5, which is 0.2. Right, so you got these two equations. Now can you tell me, for if mod of VL is equals to what? Mod of 5 into XL, right? So XL is what? 2 into VR is 1.2. This is 10. Therefore, omega L is equals to 10. L is what? 10 upon 2 pi into 60. So, what is it? Or in millihenries, it would be 26.52. So A part is correct. Right. Let's go on to the next question. So any difficulties, let me know. If you have any doubts, you can unmute yourself and ask your doubts. Okay, one more question. So here it's saying that we have two circuits A and B, and the both voltages are in phase. That means 10 angle 0 and 3 angle 0. Find the value of R for which maximum real power is transferred from circuit A to circuit B. Okay, so can we find the value of this current? We can, right? What would it be? It would be 10 minus 3 upon 2 plus R. This node voltage is 3 only. So it's 10 minus 3 upon 2 plus R, which is 7 upon 2 plus R amperes, right? Now, what is this current? I1, let's call it I1. So I1 is given by 3 angle 0 upon minus J, which is, so it should be minus J, right? So it would be 3 angle 90. Let's see. Yeah, 3 angle 90, right? So we can calculate the current 3 volt is receiving. It's I2, which is nothing but 7 upon 2 plus R minus 3 iota. Now, if we calculate the power received by circuit B, what is it going to be? it's I times square R plus we don't calculate any power associated with, because it's at zero, right? Average power will be zero for the capacitor. But for this 3 volt voltage source, there will be a power which would be the real part. So 3 iota would be zero. You need to calculate that into 3, right? So that's how we can calculate the what you say, the power that is being received by the circuit present at B. So again, so how are we going to solve it? Just equate all of the values. So 49 upon 2 plus R square multiplied by R plus 21 upon 2 plus R. And for the maximum, so you can also write it as 49R. So 49 plus 21 is 70R plus 42 upon 2 plus R squared, right? So equate, so we are required to find the value of R, right? So just equate the differentiation of power with respect to R to 0. So it comes out to be so that means 70 times 2 plus R is equals to 140 R plus 84, right? 2 plus R squared and 2 plus R will get cancelled. So that means 140 plus 70 R, 140 R plus 84. This would be what? 140 minus 140 minus 84, 56, 70 R. The value of R is what? 8 by 4 by 5, right? 8 by 10. So 0.8 ohm. So at R equals to 0.8, the power delivered by circuit A to circuit B will be maximum. So we got this. So this is three phase. Okay. So that's all for what we wanted to discuss for resonance and maximum power transfer theorems. Uh, let's discuss what we wanted to is three-phase circuits, right? So let's start three-phase circuits. So I would like to discuss first how through this diagram. So we have this diagram, and what happens is there is a stator and a rotor. In the stator, there are windings connected, uh, windings displaced by an angles of 120 degree, right? So they are connected and displaced by an angle of 120 degree, and we are taking an output from them, and we hmm, and we have a rotor, which is a permanent magnet rotor, which is rotating in the anti-clockwise direction. So, what do you think? So, as we have discussed in this in previous class for single phase AC circuit. So if in a single phase AC circuit, uh, what do you say? So uh, you move a coil. What happens? The flux lines are cut, and when the flux lines are cut, there's an EMF generation between the conductors, right? When a conductor cuts the magnetic field line. Similarly, there's a single pole, what you say, permanent magnet rotor, and when it rotates, so the conductors A dash, which is a single conductor here, the output is taken from A dash, and the A is connected to the neutral. Similarly, for B, output is taken from B dash and it's connected to rotor to the neutral, and similarly C dash and C. And as you can see, all of them are displaced by an angle of 120 degrees. So now, when the rotor rotates, the conductors that are present at the stator side cut the magnetic field lines. So when they cut it, there is a generation of EMF. So what happens? Let's say starting with VA. So we'll do VA first. So when VA it starts, reaches an angle, yeah, which is 90 degree. So this is VA, right? So it starts rotating and it cuts the magnetic field lines, and there is a production of VA. So as the north side moves towards the A, there is a strong, what you say. So the EMF production increases, and as it moves away, the EMF production decreases. And when the south pole comes, it switches the side, right? So when south pole comes, what happens? It's at the A dash terminal, right? So that's how the EMF production happens. Similarly, since all of the coils are displaced by an angle of what you say 120 degrees, right? So the conductors are placed in such a way that they are displaced through an angle of 120 degree. So at 120 degrees, the the EMF production starts in the B coil, right? Similarly, for VC, it starts after 120 degree. So that's how three-phase currents are induced in a three-phase generator, right? So now, so we discussed how the stator windings are connected and how the flux lines or magnetic field lines produced through the rotation of the rotor cut these the conductor cut these, and there is an EMF generation, right? So in a similar so there's a way in which we connect these just a second. Yeah. So there's this way where we connect these stator windings and the on the stator side. So now so that's how three-phase generation is achieved. So we'll discuss this more once we reach the part where we discuss alternators or the synchronous generators. There you will be able to better appreciate what happens inside the stator and rotor. But as of now, in a crude sense, that's how three-phase generation of current, so three-phase generation of voltage is achieved. Now, three-phase circuits are connected in two ways. So first of all, why do we go ahead with three-phase circuits, right? It's not like single-phase. We couldn't have achieved what we wanted to do with the single-phase AC generation, but the scientists or the engineers discovered that when we have three-phase generation in which the voltages are displaced by an angle of 120 degree, the amount of copper needed or the amount of wire needed to transmit the same amount of power from a three-phase circuit as opposed to that of the single-phase circuit was very less, because what happens is in a three-phase circuits you require only three wire or four wire connection, right? But if you use this single phase circuits for the same amount of power, you need to use six wires at least. So, so the scientists thought that what if we could connect them in certain way, in a three-phase way, where we can decrease the amount of or decrease the amount of cost that's required to transmit the same amount of power, and hence that's how three-phase AC generation was achieved. Okay, so let's move ahead. Yeah. So there are two ways in which the AC circuits are connected. It's star side and delta side. So this is a star connection. So this is A phase, this is B phase, and this is C phase. So and A, B, C are displaced by an angle of 120 degree. Right. Let's and there is this neutral wire too. This is PN, this is VPN, this is VCN. So if we say VAN is equals to VP, so in reference to that, VN is displaced by an angle of 120 degree and it's lagging, right? And VCN is leading by an angle of 120 degree or lagging by an angle of 240 degrees, whichever way you would like to. So how can we represent it? So if this was VAN, oh sorry, this would be VCN and this would be VBN. So this is right. So that's how these three phase. So this is one way. The other way is this is star connected or Y connected. Okay. So VAN, VBN, and VCN are called phase voltages. And there's another kind of voltage which is line voltages. The line voltages are between two phases, which are VAB and VCA and VBC. So let's for a star connected circuit, let's calculate what so how VB and VCA look like, right? So VAB, let's say. So what is VAB? If we want to calculate VAB, it's nothing but VAN minus of VBN, right? If you apply KVL around this loop of BAN and B, you'll get like so you'll get VAB is nothing but VAN minus VBN. So we know VN is represented as VP angle 0, right? And VBN is what? It is displaced and lagging by. So if you calculate it, what is it going to be? So VP angle. That's how it would come out to be, or in the polar form, it can be represented as root 3 times VP angle 30. So that means our line to line voltages are in magnitude, our line to line voltages are under root 3 times that of our phase voltages. So, sorry, I should have VL. So in a similar way, you can find out the values of VBC and VCA, and you'll find that they are also displaced by 120 degree to each other. And you can, so let's write it. VBC would be what? Under root 3, VP, it's lagging with respect to this, so it would be 90 degree, and VCA would be, this you can also calculate. Now, so line currents and phase currents. So in phase, the currents are same, right? For star connected circuits, the phase currents and line currents are same. So I phase is equals to I line to line. So this is for a star connected generation. So let's do the same for a delta connected generation. So we'll quickly do this and we'll do one or two questions based on this too. So I I would like you to, for I won't discuss delta connected generation in this class. So I would request you to go through that lecture material that sir has provided, or through that lecture videos, and you'll be able to understand it more clearly. So let's do some questions so that you know what. Yeah. So we have this question. So in this question, it's given that there is a three-phase, three-wire system which has a delta connected load. Okay, a delta connected load with 18 ohms, 100 millihenry, and a 100 microfarad capacitance in series at each phase. Assuming ABC phase sequence with 230-volt line-to-line voltages at 50 hertz, find the total power. So there's this concept in which if you have a balanced load or a balanced circuit, let's say if we represent our balanced generation, since the load is delta, let's connect in delta only. As it is a three-phase, three-wire system, so it's a delta system, right? Our loads are also connected like this. So as you can see, um, in each phase for each circuit, you can, since it's a balanced circuit with balanced loads and generation, you can represent the same thing in a per phase diagram, per phase. That is, you can convert this three-phase circuit into a single-phase circuit. So that is, there is this voltage source connected across this Z impedance, right? So now it's saying that, okay, hmm. So let's quickly calculate the value of Z. So since it's per phase, right? So per phase, it would be 18 ohm plus J times. That means it's 0, right? This would be equivalent to 0. That means our RLC load is kind of resonating because the equivalent imaginary part is approaching to 0. So that means that means cos theta, that is the power factor, is unity. So the power in three phase, what would it be? It would be 3 times the voltage divided by the resistance, right? So if we calculate it, it comes out to be 8816.67 watts, which is equals to 8.81 kilowatt, right? So that means the answer is A. So that's how you calculate the questions related pertaining to three-phase circuits. You can when it's balanced load or balanced circuit, you can convert it into a per phase solution and then check for it. And then while calculating the the power, just multiply it with 3. So it's in a three-phase circuit, the power would be multiplied by 3. So we'll continue from here in the next class since we don't have time left now. So I'll quickly go over what we did in today's class. So in today's class, we discussed some concepts pertaining to parallel resonance. Then we discussed what is quality factor and some relations of quality factor with respect to different quantities. And we checked what is the bandwidth of that the what is bandwidth and how quality factor could be calculated from bandwidth and resonant frequency. We also went through and discussed how to get maximum power, what is a maximum power transfer theorem, and how would it look for different cases. And then we did some questions pertaining to these, and then we started discussing three-phase circuits. I discussed three-phase star connected circuit. You can do the same thing, or you can follow Sir's note for delta connected to. I won't go through all of that because it would be too hectic and it's time taking. We discussed the question and we'll continue from the next class. And if there are any questions, feel free to write them in the chat box. Thank you.